Well, today we will review the necessary contents for deep learning. So we will review the backgrounds, concepts that would be required to learn this course. So what we will take a look at include, let me find a way here. First, linear algebra, take a concept that are necessary for deep learning. I will also cover some code, but I'm not going to switch to Python to code to provide coding, but you can see the logic in the coding that I used. And we also have certain information that are necessary about probability and information theory. Right? Even though deep learning models mostly rely on the technique itself rely mostly on the linear algebra and the technique to optimize the model parameters, but some of the techniques, since it is also part of the machine learning. Right? Machine learning is about summarizing pattern in order to associate with the event. Right? And to associate with the event, you need to have certain measurements of uncertainty, and that's why we have probability coming in. And also the measurement of information in the model can be done done with respect to the information theory. We'll take a look at that. Okay. You don't have the lecture 2 file? I thought I uploaded, but in any case, I'm going to upload it now. Sorry. Oh yeah, I forgot to upload that. Sorry. It's done days ago. Let me put it over there. Teaching and deep learning. Lecture 2 reviews on reviews is good like that. Okay, I'm uploading the file to the group. Okay, you can download the file from our Facebook group. Alright, okay, let's begin. Since mostly today will be about the review, if you have questions, feel free to ask either through the chat or to the Facebook group. And the content would be quite fundamental, quite rudimentary in terms of the content itself. Many of these you would probably have learned it in your undergrad level, and even some in the graduate level you may have already seen these. If you read the papers on deep learning, we find that these notions are quite necessary in order to understand the underlying idea of those techniques that they employ, right? So that's what we are going to look at in this tree. Let's start with linear algebra. We'll start with the simple one, scalar. You already know scalar. Scalar is just a number, right? Usually in the equation, it would be written as a small letter, or depending on the author used. So we can use to define something like S to be a set of R, to be from the set of R, and that would mean that S is scalar, defining real value. N is like a set of N here, that is like drawing from a set of natural number, the counting number. So this is scalar, right? For when you have multiple value of the scalar value banded together in forms of a table, right? We can think of that as a matrix. A matrix is a set of scalar values, a set of elements that you can organize them into a rectangular format, a row and columns. It can be written as like A equal Aij. This is drawn from the domain of R. This means real values with the dimension of m times n, and it often looks like this one, a matrix. So in a matrix, we can define the concept of order in the order of matrix. Like matrix can has 3 rows, 4 columns, looks like this one. It means that it has like 3 rows and 4 columns. Right. So understanding this, you understanding the concept of representation of data. A matrix is a square matrix if it has the equaling number of rows and columns. Right. And there are techniques that requires equal numbers of rows and columns, such as PCA, right, the principal component analysis, or if you want to have the graph representation. Represent the graph using the adjacency matrix. So you need to have a matrix that have the number of rows and columns equaling to one another. Okay. The special type of matrix, this is called diagonal matrix because it has the values in diagonal elements. The rest are 0. You can have the upper triangle and the lower triangle, upper triangular matrix and lower triangular matrix. The use of these type of matrix are, for example, in the distance matrix. In the distance matrix, you want to compare each element together, but you don't have to repeat twice. So you can use like it can be represented in these terms. Scalar matrix means just the matrix that resembles scalar, or basically it's just a scalar value multiplied by identity matrix. So this is like 3 multiplied by identity matrix. And for identity matrix, this is a matrix that has the value of 1 in the diagonal elements. Okay, and each of these, actually we have learned this for a long time ago, since I think since the high school level. Right? And then we have made use of it in various places, and for now, for this course, you will have to use it again, definitely, right? And you will see the roles of matrix multiplication, the roles of the usage and understanding of matrix in deep learning later on in this course. Okay, let's review Python code a bit, how to manipulate and use the matrix, right? You can define the matrix by using NumPy array, np_array, to define the matrix. You can also create a matrix or one-dimensional matrix, which is called vector, using a function from NumPy, or you can define that yourself. And for example, this one, it will create a one-dimensional matrix or a vector, starting from 0 to 15. Right? 0 not more than 16 at 1. So we have this one. If you check x.shape, you can see that the shape is 16 and comma. This means that it doesn't have the definition of column yet. You can think of this as one-dimension vector. It is not row, it is not column vector, it is just one-dimension vector. And for library like Keras, it need to have a proper specified format, like the vector need to be like column vector. So specify it like this would means that you didn't specify it as row or column. All right. For this M is 2 by 2 matrix. 2 by 2 matrix would have 2 row and 2 columns, just like that. So these are the matrix definition. You can also create those special types of matrix, like zero matrix. You can use np.zeros and then specify the order 5, 5, and then you've got 5 by 5 matrix. When you specify like np ones and 4, 4, you've got 4 by 4 matrix. If you use np.identity, then you have the identity matrix, and this would be the order of 3 elements. The identity matrix has these special properties that if you multiply the identity matrix with any types of matrix with the same order, you get the same matrix. Right? IB equal B, BI equal B. Okay. And in Python, you can use dot to perform matrix multiplication, and you can see that the results are the same. Okay. If we use only one column, right? Take the matrix and use just one single column out. You get this vector or the column matrix. We define the vector as a set of data, like, or you can think of it as a point of data. And in data science, vector is often used to represent data point. It is used to represent coefficients, and lots of other things, right? Like I can like the dimension or the axis of data in principal components, and in other things. Like you have with a method like support vector machines, which you need the method itself creates support vectors to projecting the data onto that. You have the regression model, which learn the coefficient vector, which you can use to dot with the data points to get the projected values on that specific planes. And there are so many other techniques that make use of vectors and matrices that way. Right? So in this vector definition, you have like a set of value, and this set of value, it would have like the numbers that are in order. So each of these would reflect a certain dimension of data. Okay. Usually we use like the elements in lowercase and the bold here to represent the vectors. Right. The representation of vectors can be, if in two dimensions, it can be thought of as the vector in planes, just like this one. If we have the matrix of one column, we often call that column vectors. Right? And if you have like vector of two elements, we define as like R square, like this one, and these can be visualized as a vector in the planes, and that means it's just like you have a points here, A1 and A2, and then vector A would point to this A1 and A2, and then you have these values in the axis, A1 in X and A2 on Y. Right? Though this seems to be trivial, but in fact, when we take a look at these further and further, we will see that X and Y here using neural network can be transformed into the different transformed domain, and the simple vector A in that domain can be learned. It can be learned. So the representation or the transformation of the data point itself can be learned through the data, and that is what it is quite cool for deep learning technique. Right. So for example, we can have the vector in two elements like this one. In R cube, in R to the 3, right? If we have a vector that is in R to the 3, it would have the dimension of 3 times 1 column matrix like this one, which contains 3 elements, and we can visualize it as this picture. That is, we have this red arrow pointing to this point, and this point, if we project this point back to the axis, we have lists 2, 3, and 5, right, in the respective axis here. Right, these are the vector and matrix. Now let's jump further to something a bit unfamiliar, maybe unfamiliar to you. I would say, particularly in deep learning, not in physics. Right. Sometimes we need to have an array that is represent more than just 2 axes, more than just 2 dimensions. Okay, and instead of in that case, an array can be arranged into the grid, and we often note it as using this typeface bold A, just like this one. And if we extend that the number of dimensions further from just 2 dimensions to say 3 dimensions, then we can identify the elements in A by using a certain coordinate I, J, and K, and or we can write as A, I, J, and K, and that would create the something that looks like this. We have this, and I would be the index in this direction, J for this direction, and K would be an index that is used to index the data, the location in this direction. That means we can use I, J, and K to index the value in this cube, and the value itself would look like this one. Suppose that say this is 3 by 3, right? And these are like 2, so we have something that looks like this. looks like this. And for each block, it would store the value. So, and this is in deep learning. This is referred to as tensor. Right? We can have the tensors in one dimension tensor. For 2 dimensions, we have something that looks like an array, a matrix. For 3D tensor, we have something that looks like this one, like cube. That is, it is the 2 dimension with multiple layers. For 4D tensor, we have the block in 3D that is arranged in, say, in multiple rows in the axis. Well, you can think about it this way. This is axis 0. Oh, sorry. This is often is the way that it is referred to in Python. That is referred to this as axis ID 0. Axis 0 go this way. Axis 1 go this way. Axis 2 would move on that direction. And now you can see that we have again axis 3, axis 4, and axis number 5. Well, very similar, right? But with a thicker combination of the. Let me see. Okay, right, with a thicker combination of the cube. Right. This is tensor in the sense of TensorFlow, deep learning, right? But if you take a look at the concept itself in physics, the tensor definitions would be different from the one we use here in the mathematical definition, right? But since it is more than just 2 dimension, it is referred to as the tensor. Oh, how x1 and x4 and x4 are different. It's true, right? Well, think about x1 as moving just inside. To explain this clearly, you need to think about how would you define three-dimension matrix. Let me maybe start the two title here. And then you see what I'm talking about. Let me start to write the notebook. Right. And then maybe I'm going to jump into document, workspace, deep learning. And let me create a new one. New folder. Title will be fine. Okay. So let's take a look here. I'm changing to this one. Right. Let's use NumPy. All right. I'm not going to define a matrix A. Okay. This matrix A would be two-dimensional matrix. Let's say 1, 2, 3, 4, 5, 1, 2, 3, 4, 5, and 6. This is A, right? 1, 2, 3, 4, 5, 6, and then I will use np dot the array. A. Right, this is A. Now, if I here, you can see that the axis 0 is actually the first layer, right, that we refer to here. So by referring to the number in axis 0 like A0, right, we kind of refer to, and A1, we kind of refer to the whole list of A. Now let's define another matrix to be a bit more complicated. Say I got let's say a square. This is a1, a2, a square. And I'm going to just use np dot row stack of a and a2. Alright, doesn't really have that much detail. Never mind. Or maybe I'll do this. Let's say I've got b here, and b would be 1 and 2. I use this like this one. 1 and 2, 3 and 4, and then out, and then again 5 and 6, 7 and 8, and another 9, 10, 11, 12. Okay, and then let's take a look at b. np.array b. Here, this is b, right? And if we take a look at each of the axis index that NumPy use, axis number 0, if we use b, refer to b only 0, and then you can see that we get these whole things. Right? That means if I were to use index 0 to select, even though I have this 3-dimension data, what I would have would be the whole, I would say the whole slice of data. Right? B0 refer to as selecting just the first row, so I will have just the whole slice here. But if I use B 0 and 1 and 0, let's say B0 and 0, and like this one, this index, B, I use B. Oh, I forgot to assign B here. That's why. Okay, so then I use B0, I got something like this one. If I use B0 and 0, right, just 0 and 0, then I get another slice of 1 and 2, right? And by this I did specify the first axis 0 and axis 1, so the remaining would be the variation in axis number 2. It means that I just select this one, and what I get would be the remaining in this direction. Right. So the question that you asked me on what are the difference between the first and the fourth, this would be something that is similar to what I just did. Actually, it's not like it is actually row and columns here, because to tell you the truth, Python in computer doesn't really care whether that is actually cube or what. But these are the things that we imagine, that it looks like this one. So to make human comprehend number in multiple dimension easier, so we think of it as a line, an area, and a cube. And this would be a stack of cube in one direction, a stack of cube in another direction, and so on, like that one. So computationally, it doesn't matter. It's just another layer of data. That means the fourth is actually totally different from the first one. Okay, just go into more detail, right? So x of b are 3. The x of b are 3. Oh yeah, I did not switch back. The x of b has three axes, right? Yeah. Because if we look at b, you can use this ndim, nb, ndim, nb. yeah, tell you that there are 3 axes, 3 dimensions, and that dimensions has this shape 3 by 2 by 2. Okay, and when we look at 3 by 2 by 2 in this, you can see that here is 3, the first batch, and by 2 mean these 1 and 2, and by 2 mean inside another 2 here. So these are the 3 by 2 by 2 in terms of the shape. Okay, this is quite tedious, and especially when we deal with library like Keras. There are certain times that we have to reshape the data so that it reflects the shape required. Like the first index must be index of sample if you want to use train on batch, something like that. Okay, the question from Intat, what is the difference of array from NumPy and normal array? Okay, so I think you want to ask what are differences between NumPy array and normal array. Say if I divide like this one, A C equal 1 2 3 4 5 6. This is not an array. This is called a list. Okay, if we use type C, then it will tell you that this is a Python list. In a Python list, you cannot do this. You cannot use C+1, okay? Because this is a list. A list can be concatenated. Right? You can use C and then plus and then here, the basic Python, and then 1 here, you get this. If you want to do any processing with the normal Python, what you need to do is to write something like a for loop or use the list comprehension. For example, I can do this for x in C, and then I would do like x star 2. What I get would be the square of the vector C, right, for each element. So you can read this as this would be x square, x to the power of 2. I should use star x to the power of 2 for each x in C. So this is basically the loop inside the list, and this is the way that if you want to perform any calculation in using simple Python, to do that without using NumPy. But when we use NumPy, we have to convert the list into a NumPy array. Right? For example, if you type and then look at B is numpy.nd array. NumPy array has this amazing property that is you can just doing this add 1, add 10, right? And then it will do it would add the data, the value would be added to this. Okay, I think I have a bit of review here when we review linear algebra. I also have this review of the use of Python here. Okay, but feel free to ask. It's good that you have questions. Right, normal matrix can be changed in terms of row and column. This is called transposition. Transposition is a simple transformation from column to row, right? So when you have something like 1 4 2 like 1 2 3 4 5 6 like this one, when you transpose this, the first column will become the first row, the second column becomes the second row. This is transposition. The basic transposition can be done using np.transpose, and this would change just like what I did there. Okay, so you can see here a little bit of the tweak in Python that I use. I define m to be a range 0 to 6, so it is actually 0 1 2 3 4 5 6 element. And it is actually that it actually doesn't have shapes, right? So it means like it's just an array. So instead of defining a matrix, so what I did here is to just specify the shapes, right? Shapes and minus n2. Minus mean unspecified. So what I did here is that I did not specify the number of row, but I specify the number of column to be 2. So it would arrange the data into 2 columns and the number of rows equals to the number the length of element divided by 2. I get this one. And after that, np.transpose will perform transposition. Simon asks, can we set a data type of numpy array? Sure, right? You can convert. You can set using the numpy, the function array. You can use as type to convert I think as type. I don't remember, but yeah, you can convert the data type. You can specify data type as well, right? Check the manual. There's a way to do that. Right. Now let's move on to still simple. You see that today's lecture will be the only simple lecture throughout the whole thing, right? Even when we look at the concept of right, the one that we use libraries, still we have to take a look at the detail, mathematical detail. Okay. Let's look at the matrix operation. The first one, addition. Right? When you perform addition, oh, sorry. I thought I switched back. Sorry. So since this one, right? Sorry. So transposition, right? Transpose change from column to row. Okay. Yeah. Please warn me if I forgot to if I forgot to change the slide. Sometimes it happens, right? Okay. This is transposition. This is what I said. Right? We can specify m.shape and force the shape, or you can use the reshape function in Python as well, and that would reshape the array or the matrix into the size that you specify, given that the size is okay for the number of elements that you have. Right? Addition. This is simple, so I'm going just to go pretty fast here. If you want to add an array matrix A and a matrix B together and resulting matrix is C, you just need to add each element. So Cij equal Aij plus Bij, just like this one. This is adding one to another. So the blue, the green ones are this is the result. Right? You know this already. By adding each element, you should add the proper rank. Now, the next one is more complicated, but you have known this for a long time. Determinant. What is determinant? Right? Determinant is how to calculate determinant. You have learned that in your high school. Like you can multiply it down, and then you get at the plus value, and then multiply up. You get minus value, and combine them together. We call this determinant. But what does it mean by determinant? Determinant can be best explained when we think about 3D, when we think about in terms of something like computer graphics. You have a set of points, and you have these something like projection or orientation of a camera, and then you need to transform the points onto the another plane that or we should call that an observation plane, right? And this means that we need to have a set of coefficients that multiply with the value that we have, x, y, and z in three-dimensional model, right? And that would change it into another set of points that would belonging to the perspective or the direction of the camera. Let's take a look at this video. I will share a voice. Let me find a way to share that. Share computer. So, alright. I need to optimize for video sharing as well. Let me.
Let's go back to the basics. Determinants. Let's take a matrix of 1, 2, 0, 2, 1, 0, 0, 0, negative 3, and let's use this matrix to transform every vertex on a unit cube of length, width, and height 1, aligned along the x, y, and z axes. After transformation, you'll see that we have a completely different height.
Let me add a bit here. When the presenter said about transformation, what does that mean? you need to think about each of these points as the x, y, and z point. So that means for each of these, it has 3 set of values, right? And by that, so you need to multiply each of these to a set of x, y, and z. So the new value of x would come from multiplying this to the coordinate. The next value of y comes from multiplying this second row vector to the coordinate. And for z, multiplying the last row vector here to the coordinate. And then you have the new values, all right? And that's called transformation. Sometimes in image processing and computer vision and in image processing and computer graphics, this transformation is called the adverse transformation because you are creating the new set of points based on the existing point, right?
1. Aligned along the x, y, and z axes. After transformation, you'll see that we have a completely different object than we had before. But now I have a bit of a question. How much larger is this new transformed object? We could solve this problem with numerical integration by encapsulating both objects in a larger cube and
how much larger? That's the key question to understand determinant. We have the original cube, and then after multiplication, the cube becomes larger.
Forming Monte Carlo integration. After integration, we can say that the larger object is about 9 times bigger than the unit cube. Now, let's think of this problem a little differently. During matrix transformation, most vectors will stretch and rotate. However, there are certain vectors that only stretch and do not at all change direction. These vectors are known as eigenvectors, and the amounts by which they stretch are known as eigenvalues. If we align the sides of our unit cube along these eigenvectors and perform a matrix transformation on each vertex in the cube, we'll find a rectangular prism that has not been skewed at all. This makes finding the ratio between the new transformed object and the original unit cube kind of trivial. It's simply the length times width times height of the new cuboid. Now, because we align the unit cube along eigenvectors, and each side of the unit cube is of length 1, after transformation, the new length, width, and height are all eigenvalues. So how much bigger is the object after transformation? Well, it's simply a product of all of the eigenvalues, which, in this case, is exactly 9. Here, I suppose it makes sense that any object's volume will increase by the amount of stretching in each dimension, which is exactly what we said before. The new volume is a product of the eigenvalues. Now, at this point, you might be thinking that we're pretty clever, but mathematicians have at least one more trick up their sleeve. Determinants. So let's do it. Let's find the determinant of our transformation matrix. It will be 1 times negative 3 minus 0 times 0, subtracting 2 times negative 3 minus 0 times 0, plus 0 times 2 times 0 minus 1 times 0. Which is equal to negative 3 plus 12, or exactly 9. The same as we saw before. And that's...
Alright. So basically, you can think of determinant as the scale that would scale that the scale of the transformation that would scale the values in the eigenvectors direction. And then it will change. It kind of change the amount or the volume of the points in that region. Okay, so here determinant is basically you can think of it as the volume nu divided by volume O. If you think about those as the point, that means it can become larger and smaller depending on the determinant. Right, so that's the something like the rationale underlying determinant. This course we probably wouldn't use it that much, but if you take machine learning, just the basic machine learning course, and that would matters. And some of techniques like singular value decomposition make use of determinant in order to solve the model. The technique like dynamical systems also use that to solving differential equation as well. For this course, linear algebra here, on the face, no, not that much. You will see that later on. Okay. So determinant can be calculated using the NP linear algebra determinant, and then calculate this determinant for you guys. So we have one comment. Determinant is a mirror reflection point in determinant is that a mirror reflection point in the graph representation. No, I would say that it is more like a scaling factor. A scaling factor at the eigenvectors axis. So just from the data that you have, when you multiply or transform that data using the matrix that you have, it would transform the data into the new dataset that is scaled depending on the determinant of that. One obvious example is I think is the when we use image filtering. Right? I think that is quite a good way to do. In image filtering, if you use the image kernel like this one, which when you calculate the determinant, this is actually 0, and actually the sum itself is 0, right? Oh no, yeah. So yeah, this is more like in terms of the sum rather than that. So yeah, it's a scale of the eigenvector in the specific in the specific direction of the eigenvector. Eigenvector is the I would say the axis that indicating the variation of data, that the data vary in that direction. We will consider that when we learn concepts about autoencoder. And if some of you have taken the course in text mining or have been familiar with the concept of text mining, there is a method called singular value decomposition, which also decomposes the data, or the PCA, principal component analysis, that decompose the data toward eigenvectors, and you kind of project the data points onto that axis instead of the original one to reduce the dimension of data. Right? So yeah, for determinant is the scale function, the scaling factor of that. Okay, the basic operations in the linear algebra here. When you have matrix, you can multiply, add, square it, and find the what is it called? The modulus. Okay, all right, and the division, and you can add simple matrix to that, and you can also add this 3 and 4. But this is quite strange, right? If you take a look, m is 1, -1, 2, and 0. So if I write, it would look like this one: 1, -1, 2, and 0. Why we want to add this with 3 and 4 and reshape to have just one column, and that would mean we have this 3 and 4. We know from basic linear algebra that we cannot do this in mathematical sense, but for Python, right, it has the functionalities that would allow you to add the matrix with different dimension together, given that you can add another axis, given that you have one axis satisfied. For example, for this one, we have the axis number 0 equaling to one another. That means for axis 1, what happened here is that Python would just increase another axis by repeating the same pattern, 3 and 4 here. So we would have 3 and 4, 3, 3, 4, 4, and then adding to the above here. So we have 4 and 2 and 6 and 4. That's why we have the result like this one. Okay, this is called broadcasting. It's a mechanism of Python that try to make things easier to write a program. Okay, broadcasting. I think we will have a slide later on about this. Let's move on because we have like 120 pages to go over, a lot of them. Matrix multiplication, okay? Multiply two matrices together. This can be done by multiplying row matrix with column matrix. It's actually not multiplication per se. It's the dot product between the row matrix and the column matrix. And this dot product would result in the projection between this row and column, and then you get the resulting matrix value here, right? Matrix multiplication has these properties. That is, it has these associative properties, but it does not have the commutative property. You cannot switch place. Okay. Perform matrix multiplication in Python that can be done using matmul, numpy matmul, which is faster than numpy dot. We can look at the reference why that is the case, right? So here I got this matrix 2 times 3 and 3 times 2, multiplying resulting in 2 times 2 because using the first row matrix 1, 2, 3 and dot with 1, 0 and 1, you get 1, 0 and 1, resulting would be 1 plus 3 equal 4, okay, and so on, doing that matrix multiplication. Okay, deep learning requires a lot of matrix multiplication. That's why relying on the CUDA library, the deep learning library, is a good choice in order to accelerate the computation. The library like TensorFlow and PyTorch relies on the basic CUDA library to use GPU. That's why in order to train the model using the GPU card, you need to have the NVIDIA GPU that contains the CUDA cores, and you can utilize that to perform parallel processing, parallel computations. Multiplication of matrix using by doing CUDA programming is actually faster, a lot faster than using CPU, right? But I use CPU here, and also in your lab we use CPU as well, right, for simplicity's sake. Okay. Right, let's move on. The matrix, if we have a square matrix, right, the matrix would have the inverse. It is invertible if you multiply another matrix C to A and then you get I, right? And that's apply whether you multiply C to A or A to C and get I, the identity matrix, right? We call this inverse matrix. C is an inverse matrix of A. Right, when you have the result like that. Finding inverse matrix in Python is easy. I'm not going to teach how to do that because it's not the main purpose of this course. Inverse matrix, you can use np.linear algebra and inverse to find the inverse matrix. And when you multiply the M inverse with M, you get the identity matrix. Okay, let's move on. From the matrix, now we take a look at vectors. A vector is just like one column or one row of the matrix. Operations of vector can be looked at, well, most of them are similar to matrix. Right? Like when you multiply the scalar value, scale the vector, it multiplies to every element. When you add vectors, you need to have like equal number of elements, and then it will result it like this. When you perform this, a dot between vectors, this would multiply the elements in the same dimension together and then combine the result. Dot product is important, especially when we trying to find the cosine similarity between two vectors. This is actually an essential technique in text mining. When you want to have, when you want to compare the two data together, instead of using Euclidean distance that compare the size of the distance between 2 points based on just the difference between values alone, you can compare it in terms of the cosine distance, which compare the distribution of the values, and that's usually the way to do text, the natural language processing in terms of comparison and others. So dot product plays a major role in that. The reason is because the dot product formula has the cosine elements in that, right? Vector would also has these properties in terms of the norm of the vectors, right? The norm here refers to the L2 norm. L2 norm is the size of the vector when you take a square of each element and then take a square root. This is L2 norm. Right? So in all, why does it called L2? It is because like you think about this as two dimension, drawing a line between 2 points and then you try to find the length of the line. Right? So that's two dimension way of thinking, and we kind of trying to calculate that length in line, the L2. Right. Okay. Now instead of thinking of metrics as just metrics, let's think of them as part of the equations. We often find this when we do machine learning. When we perform machine learning, we would have the unknowns and the data points, the idea is to estimate the values of the unknown based on data points. And in order to do that, many times we need to solve these systems of linear equations. When we have the two equations like this one, 2x plus y equal 100 and x plus 2y equal 100, it's just like we have two lines. And these two lines would kind of intersect with one another. And the intersection point is actually the solution of these two, because it would be the point that satisfies both equations. Okay. Now, if we think about these systems of equations, there are three possible scenarios. That is, we can have no solution at all. That is, the equation is less than the variable, or in other words, the data points, because each equation represents each data point. Data point is less than the number of parameters. You can have like one exact solution if they are equal, but this is not realistic because of what? Because in real life, things would not occur exactly. You would have certain uncertainty, certain noises, and those certain noises would create many solutions, many points, but you have a certain number of equations. And that means there are many solutions, but you need to estimate the best one out, right? And this is often the case in terms of machine learning, deep learning, that we have a lot of data set, and we want to estimate the parameters of those. So how do we solve system of equation, right? One might simply think, okay, if we have two equations, two unknowns, we just multiply it with the inverse matrix, like a x equal b. Then we multiply it with inverse of a, right, to both sides, and that's it. We have x. Okay. So when I did this in Python. We have 2, 1 and 1, 2, right? This is matrix A. And we also have 100 and 100 here. So what I did here is to find inverse of A and then multiply inverse of A to B, right? Math inverse of A and B. I got 33 and 33. This is solution, exact solution of this system of equation. But many times we are in this scenario that is, we have more equations, more data than the variables. And for example, here I use a data frame called MT cars. Right, this is the data set that used in a lot of machine learning, like a pet data set that used in machine learning course. It contains 33 data points and 11 variables, and we have one target variable called MPG as the output. Let me show you that data set. I think I should have it here. Not sure if I got it here or not. Let me find elsewhere. Should be in the clustering machine learning. No. Is that? Yeah. Copy this. to this location. Before is going to okay, let me share this. Data looks like this one. I just import that to be CSV. Right, it looks like this. It has these lines, or you can think of this as index column, row line, and the others are the spec, like the MPG. This is mileage per gallon, the fuel efficiencies, and the spec of the car. Right? So there are a number of data points, and we want to estimate this when you know the spec. Okay. So the data itself has 32 data points, 11 variables, and one variable to predict means that the rest of 10 variables, we need to use them as predictors. In this case, we have more equation, more data points than the unknown, just 10. Okay, so how do we solve this? Let's take a look at a simple equation here. We have like a data set like this one in the multiple regression model. We have x1, x2, and y. We want to fit this data point to a multiple regression, y equals c1, x1 plus c2, x2 plus c3. Our job here would be to estimate c1, c2, and c3 from these systems of from this equation. So in regression model, we can do it two ways. One way is to take a partial derivative of the error function and then solve it using that method. Another is to utilize the linear algebra, and then you can see that we have a set of x1, x2, and y. So why don't we just substitute x1, x2, and y onto this equation? So we know here that 12 is y, x1 is 1, x2 is 2, and that we got the first equation. And the second one would be 9, 2, and 1, right? 2, 1, and 9, right? And do that for the 4 rows. We got 4 equations, 4 equations, 3 unknowns. And this system of equation can be represented as matrix on the right hand side. The problem is that we cannot inverse this, right? Why? Why can't we? It's because the matrix is not a square matrix, right? When it is not a square matrix, you cannot find an inverse of the matrix. So mathematicians come up with a way that would allow us to solve system of equation without really relying on the partial diff, right? By using the pseudo-inverse method. The pseudo-inverse method, trying to find like this, we try to find the values of b, right? A times b, like the coefficient times the unknown, and y, which are already the known function. So we multiply. So switch side, we got a b equal y. So to get b, we have to make a become something that is square, so that we can find the inverse matrix. How to make it square? We can multiply it with the transpose, right? Multiply a with a transpose, and that would make this part of the matrix, square, right? Because suppose that we have, say, suppose A, we have it as the matrix of 5 times 3. If we multiply it with 3 times 5, we will get a square matrix as a result. Okay, so multiplying transposition of the matrix to itself give you the square matrix, and because this is a square matrix, you can find inverse of it, right? This is an inverse of square matrix of A transpose times A. And multiplication of inverse with itself will give you an identity matrix. And multiply with B, you get only B. Right? And this the right hand side is the solution. So I demonstrate this by using the data point that I have there. I got matrix A like this one. This is a matrix B, which I need to reshape it in order to make it a column vector. And then what I did here is that I use this PINV, a little sheet here, but you can also do it. But yeah, I have the other slide to show you like full form, right? PINV, this is pseudo inverse of A. And multiplying pseudo inverse of A to B, you get an array equals 3, 5.5, and minus 1.5. Remember this. We will take a look at the full form on the next page. On the next page, I did what I show you there, the pseudo inverse. So this is the inverse of A transpose times A transpose times the value, right? We get the value of the result as 3, 5.5, and minus 1.5, similar to what we get when we use the pseudo inverse function. Okay, and another way is to solve this is to use the partial derivative. That is the least square method. To use partial diff to find the value, but I did not do that here. Right, so this is the way that you can solve the system of equations to find the parameters, and that will satisfy this least square criterion, which is important. Like when you have unknown, you want to find the base value of parameters, you can solve it using least square by taking derivative of the function, just like this one. Suppose you have this function. How do you find the lowest point of the function? You would take a derivative to get the gradient and then set it to 0, right? And then you get this point out. And this is the derivative of the point where the derivative is 0. So this is called the least square. The method called least square will try to find this point by take a derivative of the unknown and then set it to 0. Pseudo inverse also gives you the least square solution without taking any derivative. Right. Okay. Next is the concept of linear combination. Okay, if you have a vector v1, v2 to vp, and then you have say you have a constant c1 to cp, we can call the vector y. Y here is a linear combination of v1 to vp because it is a linear, right? Linear combination. Right? A vector multiplied with a constant add to another vector. This is a linear combination of the vector. This concept would relate to the concept called independence. That is, if you have a set of vector, this set of vector is called it would be linearly independent, right? It would be linearly independent if you cannot derive one vector from another vector. In other words, you cannot represent v1 with the rest. You cannot represent v2 with any of v1 to vp. Right? No combination of C would satisfy this equation. Okay. So if this is the case, right? This means that the vector that you have are independent from one another. In data science, in machine learning, it means that the variables or the vector that we have here are not redundant. They offer the information on their own, right? But many times we have this collinearity or the redundancy in data. For example, we can have one column indicating the salary and another column indicating the salary times 5 as the credit limit of that person. So that is the case that make that the variables are collinear. Okay, so that's independence. For dependent, right? We call it linear dependent if the solution here are non-trivial, or in other words, there are C values that would satisfy this solution. Or you can just say put V1 on the left hand side and move the rest to the right hand side, and that would make this linear combination to be independent. All right, I think it's too bright. I need to tone it down. Okay, let me give you an example here. This is linear independent. Say we have this as 1 and 0, and this is 0 and 1, right? Well, now you can see that these two vectors are independent. You cannot derive one from another. Okay, in mathematical terms, sometimes it is called orthogonal. Right? They are orthogonal to one another or perpendicular to one another. When we draw it in the plane, it would have something that looks like this. Right? It goes to different directions. Okay, so this is linear independent. You cannot combine vector to create another vector. The second one is linear dependent. Say we have something like 1 and 0, just like the last one, and we have another one, 0 and 1, but we have the third one, and this is say 2 and 2. You can multiply this, right? You can see that we have 2 here, multiply plus 2 multiply minus 1, that equal 0, right? And these are examples of linear dependent vector because you can derive this one based on the two before, right? In data science term, these variables are collinear, and if you use it, it will offer the similar information to use. Right. Another concept of in the book in this book, Goodfellow, right? You see this symbol many times, right? This is called norm. Right? Norm refers to you think of it as the way that we can measure the size of vector. Okay, so this is actually the summation of the square by p, and then take the square root of order of 1 over p here. So when we refer it to as L1, right? L1 norm. We put it in this way in this script. The x, the size of vector, and then 1. This refers to the addition of the magnitude of the values. In terms of machine learning, sometimes this is called the Manhattan distance, but this is actually the L1 norm. Right? And when we use machine learning algorithm many times, we need to set the value to whether we want to prefer L1 or L2, which will result in different mechanism in regularizations of the machine learning algorithm. Like L1 or the lasso regression would reject the variables, while L2, or we call in machine learning called rich regression, this would tend to reduce the weight, reduce the coefficient value in the regression model. Okay, so here in terms of the equation, the norm is the size, and whether it is 1 or 2 depending on how you define them. The Euclidean distance is derived from the L2 norm. Right. Unit vector refers to a vector of size 1. It indicates the direction of the vector. Right? It is used to indicate the direction of vector. As for example, these are the Cartesian coordinate vector, indicating different direction. Okay, we can find the unit vector along a certain vector by dividing that vector with the size of the vector. Then you get the unit vector, and that can be done in Python using this NP array, and then we find the norm and then divide by divide v by the norm, you get the unit vector. It doesn't mean that you add them and then you get 1. You need to calculate the size of the vector, taking each of these and then square them and then take a square root, and you get the value of 1. Right? Add them together as well. Right? This is the unit vector. Okay, let's move further to the concept of orthogonal. Right? Orthogonality. This when you have two vectors, u and v, they are orthogonal if you dot them, and then you get value is equal 0. So mathematical sense means that they are perpendicular or uncorrelated to one another, right? Just like this one, x and y. Okay, so orthogonal can be determined by the product. If you dot product the two vector and then you get 0, it means that the two are orthogonal. Okay, this is 2, 1, and minus 2 and 1. But there are certain meanings of orthogonal. Right? In data analysis, orthogonal indicate that the two data are not correlated. Okay, if we talk about text analysis, it means that the two text posts or the two text data points are these are different. Right? They are from different distributions. Orthogonal is also used in support vector machine to do the data projection. It is also used in many other technique, underlying technique of those areas. Okay. Now let's combine orthogonal with the vector along the line. Right? When we have a line like this one, 2x plus y equal 10, we can find the orthogonal, the vector that is the unit vector that is orthogonal to the line by just putting the coefficient into the vector, and then you get the vector that is perpendicular to the lines. Why do we want this vector? Right, that's the reason here. In machine learning, many times we have the data that looks like this. Say, like this one, right? And what we want is to find a line. And this line would separate the data into two parts. All right. Okay. So what we want is this line. Right? It would separate the data into two parts. In two dimension, this line would have the equation of y equal mx plus b. Right? Y equal mx plus b. Or if I rewrite this, I can rewrite it as c1x plus c2y equal c1x plus c2y, and this should equal some value, c3, equal in the value here. Alright, or it can equal 1, because we put this and then divide it with everything, you can have 1 here. So that would be coefficient of the coefficient in front of x and y, and we can use this coefficient to determine the vector that is perpendicular to this line. Why do we do that? Anyone can give me some idea why do we want to find this vector that is perpendicular or orthogonal to the line? Why is that? Why? The reason is because of this picture. No, I should. Say we have a small vector here, and we have a large vector here. This point. You can make a projection to this, and that will give you the vector component along a particular axis, right? If you project or dot product of this x with this u, right? X dot u, this is x dot u, the component of x in the u axis, or you have projected the point. You have project the point onto the plane. So if we perform that here, it would be like this. Suppose we have this. So that would mean we are trying to project, this is the plane, this point onto this, and this point as well onto this, and this point as well onto the plane here, and this as well. Same go for this one. And as a result, you can see that the projection of the point with the vector along the vector orthogonal to the line give you a lower dimension, just a one dimension of values, and then you can separate them with just one threshold, right? Think about this just like many of machine learning technique, that when you use the model, it gives you probability, right? That's the result of projection, and then you can use the cutoff of probability to determine which side it should belong to, right? So this is the root of those techniques. By projecting the point onto the plane, you are now trying to classify the points based on the lower dimension of data. Many of the deep learning technique, neural network, also perform something that is quite similar, but without the handmade vector, without the handmade feature. We actually let the algorithm learn how to transform the data so that it performs this projection by themselves. Okay, that's the first part. So many parts here. I don't know if I can cover them all. What time is it now? About half. Right. Right, let's take a look at this first before we take a break. Right. The next concept is eigendecomposition. Right. Eigendecomposition can be used to determine I would say the low resolution or the core component of the data. Right. Let's try to understand what are eigenvectors and what are eigenvalues first by taking a look at this example. This example indicates the unemployment, right? The change in the unemployment rate over time. Okay, we will use this mathematical model called Markov model. Markov model would describe the change of the population over time. We can use it to explain the change of those infected with COVID and those that are susceptible to COVID, and create something that is called the susceptible infected and recovery model, the SIR model, to perform prediction. Markov model is actually a probabilistic model I can use to do projection as well. Look at it this way. So if we have two population, right? If individual is unemployed, then it has the probability of P to be employed and 1 minus P to stay unemployed. If individual is employed, it has probability of Q to stay employed. All right. Okay. So we have two set, and this have to be fixed. x because x be the ratio of employee. So this is supposed to be Q, and this is 1 minus Q, right? Because if we look at this one, if individual is unemployed, then has probability P to be employed, and if he is employed, then he has probability Q to stay employed. So this is the figure, right? So here we have two populations. If it is employed this week, you can have probability P to transit to employed. If it's unemployed this week, if it is employed this week, it has probability Q to stay employed, and 1 minus P will be stay unemployed, 1 minus Q to be transition from employed to unemployed, right? And from this one, we can rewrite this as an equation. That is, xt plus 1 would equal to qxt and p yt. Right? This would be the expected value, right, of the next step. But you can multiply it with the probability or the ratio that would stay the same. And for y, this is for the unemployed. You can have the stay at y and then change from x to y. Then we can represent this as a matrix, like this one. We have vt plus 1 as the new state. This equal to multiply with a with vt. You multiply a here, p, q, p, 1 minus q, 1 minus p, with the xt and yt. We can call this a transition matrix or the transformation matrix. That would make the transition of the Vt to Vt plus 1. Okay. This is the problem called Markov model, right? It is used to study the change in the state. Markov model can be used to represent the connectivity of the graph, can be used the transition of the state or the connection between state and represent them as the probability. And we can use A to represent the relationship between them. Okay. The usual question that is asked in Markov model is what is the long-term state equilibrium? How do we know? We can determine the long-term state by multiplying like this. We have V0, multiply A, you get V1. From V1 multiply A, you get V2. And this is actually A times A and V0. So it is actually A squared V0. So on you have Vt equal A to the T V0. It means that if you compute the power of this matrix, you get the long-term transition probability, right? The long-term trend or the equilibrium of this system. Say if we have the value of P and Q like this one, 0.136 and 0.998, we get the matrix like this. Suppose we square it 100 times and multiply it with 0.95 and 0.05, what would be the value here? And what would be the value? Would this value depends on the matrix here, or would it depends on this, right? This vector that we want to multiply with. Right? In order to calculate this efficiently, instead of computing the multiplication 100 times, we can determine the eigenvalues and the eigenvectors of this A100, and we can use it to calculate in the calculation instead. So let's take a look how it works. So these are the reason we need eigenvalue and eigenvector. Eigenvalue and eigenvectors also play important role in machine learning. When you have a lot of columns of data and you want to compress it and you want to find which columns are redundant, one technique that allows you to do that is called the principal component analysis. right? Principal component analysis would analyze the directions of variations, like this figure, right? This figure, if you take a look at the data, the cloud behind here, you can see the spread of the data in the both x and y, right? So it means that something like x and y depends on one another. But if we use PCA to do that, the PCA would transform the data points from x and y here into the axis that is shown here, and that will make it the data of the two axes independent of one another, and this is a better representation than using the two axes that are collinear here. Okay, eigenvector is also used in image processing computer vision to represent doing something like face recognition. So you can decompose the face into multiple linear combination of the eigenface. These are the eigenvectors, and then you can decompose the face into multiple combination of these, and then we can use the coefficient to identify whether this face belong to this person or not by using this in comparison. Right, this is a technique called eigenface. You can take a look at this if you are interested in this. And there are actually a method that in deep learning that try to perform something similar to this one. It's called Siamese network to compare between this and do the decomposition by itself. We will use this concept as well in the autoencoder and embedding when we try to learn the embedding representation of the text. In terms of network analysis, eigenvectors is also used to analyze the connectivities of the network, right? By representing the network as a matrix, and then one can analyze the long-term transition of the matrix on which node that are likely to be the main nodes, right? That when you travel infinity times, that you are likely to fall into those nodes. And these are called eigenvector ranking. I can use that. Okay. Eigenvectors also plays part in the linear transformation as well, just like I said earlier. Just like this one, if you have like this 1 and 2, and then you multiply it with this matrix. This matrix would transform 1, 2, into 5 and 6, right? So it means that the direction of transition from 1 and 2, like this one, it will transform into something that looks like this, 5 and 6, this point. The change would be in terms of you can see that the change, although the points are changing, but the axes are still the same, the red axis are still the same, and these are the eigenvector axes. So these are the examples. They are the same in the sense that it represents like the core axis of data. And when the change occurs to the data points, these are the same but with certain scaling. Okay. So let's take a look at the definition of what is eigenvector. Yeah, let's say that we have a matrix, n times n matrix, just like the transition matrix or the probability matrix that we saw earlier. Right? We have A to be a square matrix, n times n. And in the definition of eigenvector is that you can, say you can transform A to lambda, meaning that if you have, if this occur, then X is an eigenvector. Okay, when you multiply the transition matrix to this matrix X, and then the result is X and the constant, right? We will call this constant an eigenvalues, and we will call X an eigenvector of A. Okay, so if we were to interpret this, it would be like, suppose that A is the transition, like in the graph model. A is the probability of transition. X would be a vector indicating an equilibrium, right? A stable point that you cannot change the location anymore. It would just stuck at this point, and like this one, right? It is stuck at this proportion, and A would change to lambda. Okay, does this things exist. Let's take a look here. Suppose we have a to be 1 minus 1 and 2 and 4, right? We can multiply 1 minus 1 and 2 and 4 to 1 and minus 2, and the result would be 1 and minus 1 times 1 and minus 2. So this would be 1 times 1 and minus 2 times minus 1, right? That would be 3. The above here would be 3, and down here 2 minus 4 and 1 minus 2, and this would be 2 plus minus 8, which is minus 6. So we have here minus 6. Factor out, we have 1 and minus 2 and 3. You can see that these are both 1 and minus 2, and 3 is a constant, right? So 3 is an eigenvalues of A, and 1 and minus 2 is an eigenvector of A corresponding to these eigenvalues. Okay. How to find these eigenvalues? Right? Mathematically, this can be determined by moving the lambda x to the right hand side. Moving lambda x to the right hand side, we get a minus lambda I and x equals 0 as an equation. Right? This equation will be non-trivial. Right? Will be non-trivial. This again refer back to the concept of determinant. What is determinant? Right? The signs of transformation. Okay. So only this could satisfy the equation, because x cannot be 0 anyway. It must have certain values. That means this multiplication need to be 0, but itself cannot be 0 because a is not 0. Lambda I, how can it be 0, right? So that means the size, the transformation has to be 0. The determinant has to be 0. So this will be the determinant of a minus lambda I has to be 0. And that's the reasons that we learn in, I think this should be in the calculus 3, I think. Right? Calculus 3, that when you have system of linear equation and then you want to find the behavior of that, you need to calculate the characteristic equation. A characteristic equation is calculated by arranging in the matrix form and then put the lambda in the diagonal and then calculate the determinant, just like this one. We have a 1 minus 4, 1 minus 1, 2 and 4, and then I have here lambda and then the I here. And combine them, I have 1 minus lambda and minus 1, and 2 and 4 and minus lambda as a minus lambda I. And then we can calculate the determinant by multiplying down and multiplying up. Multiplying down, you get positive value. Multiplying up, you get negative value. And then you add a negative modifier there. Right? So we have multiplying down 1 minus lambda and 4 minus lambda. Multiply up, you get minus 2. Add the minus, become plus. You have plus 2 here. Right? And then multiply together, we get lambda square. And this is 4 lambda, this is minus 4 lambda, minus 1 lambda, you get minus 5 lambda, and 6. Then factor this, you get lambda minus 3 and lambda minus 2, right? Because multiply equals 6, add equals 5, this is 3 and 2. Okay. And this results in two eigenvalue, right? 3 and 2, right? These two eigenvalue. Then from these two, we can use them to determine the eigenvector by substitute 3 into the above and substitute 2 into the above and then multiply with x. Right. So we already know this, that we have this relation a minus lambda I equal x. So what we can do is to substitute lambda equal 3, right? We know lambda equal 3 is one of the valid eigenvalues. Substitute lambda equal 3, then we get this matrix minus 2, minus 1, 2 and 1, and x1, x2. Right? When you multiply this minus like say 2 and 1 and x1, x2, you get this 2x1 plus x2 equals 0. Right? And say if you move x2 to the right hand side, then set one value, say x1 equal 1, then x2 will be minus 2. That results in this, right? 1 and minus 2. Now we can do the same thing, right? Replacing lambda equal to in, and then the result will be eigenvector of 1 and minus 1. Okay. Let's see if I'm correct here, right? I can use numpy, and then I can use numpy, and then using NP linear algebra dot eigm. This will find the eigen value and eigen vectors of matrix M 1 minus 1, 2, and 4. Result is EV and EG, right? EV here is 2 and 3, right? Just like we computed. And for eigenvalues, these are the unit eigenvalues. That means kind of have unit size divided by the size itself. So here the first one is the first one here, minus 1 and 1. Okay, just like this one, minus 1 and 1, 1 and minus 1. Okay, this is for the eigenvalue equal to. For the eigenvalue equal 3, we have this 0.44 and minus 0.89, right? This is for this one, 1 and minus 2, right? 2 times that, right? So these are the concepts of eigenvalues and eigenvectors. Eigenvalues and eigenvectors are the I would say the core concept that allow you to decompose the data and reduce the rank of data into the lower dimension of data. The technique like topics model relying on that type of concept. And I think when we do the autoencoder, autoencoder will try to kind of compress the data into lower dimension. It is also the case here as well. All right. We will review the content when it needs again, right? But these are the topics of eigenvalue, eigenvectors, and the linear algebra required for this course. Okay, so far as I can review, right? So there are still other techniques that and other things that I cannot review, like the matrix decomposition itself. I cannot do that. SVD, singular value decomposition, I haven't done it here. But well, I think these are the basics we need right now. Okay, let's take a break for 10 minutes, right? And then we will come back to this probability theory, right? And the information theory part of this lecture. Okay. This lecture is quite jam-packed. Last year, I spent 2 weeks for these two review, but I think they are too much. Although you probably require 2 weeks and go in slower pace. But since these are reviews, I would like to go a bit faster. You can review the content later on, and I will encourage you to do so. In the book here, it also contains this first section, which contains the linear algebra, numerical computation, linear algebra, and the probability and information theory should be in the first, I would say the second and the third chapter of the book. This is what I review here, right? Okay, so you can read it afterward. Okay, the second half of today's review will be about probability theories and information theories in deep learning. We use probability to represent uncertainty in the data. And whenever there are certain unclear statements, we need probability to be a framework to represent those uncertainty. Okay, so that means when developing AI, if we want AI to represent human, we know that human has uncertainty in the actions. AI has to also capture those, especially the data from those, and then trying to figure out the types of reasoning, the types of patterns in the data, reducing the uncertainty down. The source of uncertainty in the data can come from the model itself, like coming from the system. It can come from the observable data. it can come from the model that we use. So it can come from many types. The idea is to use probability to represent, to reduce and represent those. Okay. There are two ways to represent probability. The first one, frequentist. A frequentist model represents probability as observations. Giving a number of observations, we can find a probability P, which are the proportion of the event that occur. But this kind of reasoning may not be applicable. For example, if we were to assess the risk of reactor failure, since the reactor may not have been failed before, so this has not occurred before. How can we know that there's probability for that to occur, right? So frequentists would fail in this regard. On the other hand, Bayesian probability, right, use the probability attach itself to every event, and not so for each event it does not have just one or two outcome. It doesn't have like whether to have flu or not have flu, right? For each person there is a probability to have flu, right? And then those probability will be updated once we know more evidence. Okay, so this is called the Bayesian probability. Machine learning use the Bayesian framework to calculate the probability based on the data or the evidence that are presented to the model. Random variables is a type of variables that has probability attached with it. For example, we can have random variable with two choices, shown and unshown, or as a count number of cars passing through the gate per minute. Each of these value would have the probability associating with the value itself, or it can be continuous. Okay, when we have random variable and then we try to understand the pattern of random variables, we can explain the distribution of the value of random variable as the probability distribution. The probability distribution is used to describe how the data distribute when we take a look at the data as a whole. For the discrete value, right, we can have the probability mass function, which is the probability distribution of the discrete variables. For example, if the variables can take the value of 1 or 0, then we can have the probability distribution looks like this. That is, suppose we consider the event of customer churn, customer leaving the service to auto company, for example. We can have x equal churn and x equal non-churn to be like 0 and 1. And each of these values would have probability associating with these types of it, right? So this is called the mass function, probability mass function. For each of the values here, we have probability value associating with them. Probability can be considered together when we have more than one variable. These are the joint distribution, right? The joint probability distribution when we consider x and y together. When we change the value of x and y, each changing here would have the probability associating with each values. And if we were to combine the value all together, it would be 1, right? And the probability would be more than 0. So these are called the joint distribution because we consider the two events x and y together, and each combination of this would like represent the chance that the two values would occur altogether. PMF or the PDF that because we are considering the discrete variable right now, that the variable here are the discrete level, has certain properties. That is, the value itself would be between 0 and 1, and the summation of the value would be 1 for all of the condition. These are for the mass function. When you have the random variable as the continuous variable, your distribution would be the continuous distribution. We would call that the probability density function, the PDF. PDF has certain property that is the value must be more than 0 and the integration of the function p has to be equal to 1, right? So you may have seen this before. This is the normal distribution curve. This is the probability density function indicating that most of the value would be located in this region. Okay, and if you integrate the area under the curve, you get the probability value of the value falling between A and B. Okay, so in the PDF, we do not just look up the value from the curve. We need to integrate the area under the curve to get the area, the values of the chance of the value falling into these regions. All right. Okay. When we have joint distribution, we can marginalize the joint. Marginalization means that we can disregard one variable to consider just only one axis alone. Like this one, we can marginalize pxy into just px by integrate pxy dy, or in discrete we can sum the probability along the y-axis. Okay, and these are the marginal distribution of the probability. Marginal distribution is used in the calculation of the subsequent theory here, like in Bayesian theory and in the conditional probability. In the conditional probability of event, we can consider the change in probability. This conditional probability should be thought of as the probability of y, right? It is still the same, but probability of y, but we know that x occurs, so it has to update, right? So in the calculation, direct calculation of the conditional prob, this is py given x. This is the joint distribution between x and y divided by x. So in terms of the conditional prob here, we have initially, suppose we do just consider PA, right? PA is the area of A divided by the area of S, that is PA, right? For PA given B, right? If we have B, we know that B occurs. What is PA given B? PA given B would be the intersection of A and B, this area, and divided by PB, right? PB is the entire area here. So this would be the A and B and PB. So this would be the proportion of, just like if we change the universe into just B and then find the part of A that is in that universe, and then this would be the conditional probability. Okay, the conditional probability has the actually this is from last year, I forgot to erase it. There is a chain rule related to conditional probability. That is, you can represent the joint distribution by the multiplication of the conditional prob of each variable, of each I. Okay, for example, from the joint prob like this, you can change it to for this one, you can change it to px and then p of this joint given x1, and then from this one you can then further split to x2 given x1, and then so on. This is the basic concept of Bayes theorem, right, in the Bayesian network theory, that allow us to create relationships between evidence and the observations and the probability update technique in that sense. But in theory itself, it means that the joint distribution can be calculated back from the conditional probability distribution by multiplying back. You can take a look at the proof by yourself later on. Okay. In statistics and probability, there is the concept of expected value or the expectation, right? The expected value is the you can think of it as the weighted sum, right? The weighted sum of the random variable. So you can just multiply the probability to the random variable, the f value here, and then you get the expected value out. Okay, so for the discrete, this would be just multiplying the weight with the values. For continuous, it would be the integration. Okay, expectation is linear. That means if you have linear combination, apply expected value in, then you get the result. You get the result as the expected value by combining the expected value in this way. In terms of variance, variance is also the expected value, but it is the expected value of the deviation. Okay, and then here you get the variance. For covariance, okay, covariance is similar to variance, but instead of calculating the expected values of the variance of the difference between the value and the expectation square, we calculate this of two variables, f and expected value of f, and g and expected value of g. We call this the covariance, if they are varying together or not. If the high value tend to pair with the high value, then you get plus and plus combining together. If the low value combine with the low value, you get like minus and minus, and combining together in multiplication way, you get the plus value anyway. Right? And on the other way as well, if you have large and small pairing together, you get the negative sign. Okay. And covariance has certain properties. That is, when we talk about the covariance of matrix X, this is for the xi and xj for the internal X. Okay, and the diagonal element of the covariance give the variance value. Okay, so basically the covariance of matrix, the covariance matrix would indicate the covariance between two vector. And if we consider only the diagonal matrix, it would give you only just the variance value. So these are the basic of stat, right? You can, well, actually the stat book might show you a simpler explanation than what is covered in the deep learning book. This book is very theoretical. That's why the representation here is quite complicated. But when you take a look at this concept in the statistic book, they are quite simpler than this one, right? Now let's take a look at the common distribution that can occur in nature, right? The first one that we often see in machine learning. The first one is the Bernoulli distribution. Bernoulli distribution is the distribution that referring to the binary random target. That is, the target can be 0 or 1. So you have the property of x equal 1 equal phi, and x equal 0 equal 1 minus phi. And that would make the property of x equal certain x. X equal other values, if x is the count of the value, equal phi to the x and 1 minus phi to the 1 minus x. The expected value of this type of distribution is its phi, and the variance is phi and 1 minus phi. Right? Bernoulli play a major role in binary classification. Right? When we perform binary classification, we are kind of model the data as the Bernoulli distribution or the binomial in the generalized linear model. Now, when we have multi-class, instead of having the Bernoulli distribution, we will have this multi-Nulli distribution or the categorical distribution. In the multi-Nulli distribution, we have like k different target to predict, and that make when we parameterize it, we would have probability of belonging to the class k, and the final, the case state probability would be the 1 minus the rest, right? So we have like the value between 0 and 1, and the last one also between 0 and 1, basically just like that. So, but the multi-nully refer to the multi-class classification situation that we often had when we perform machine learning tasks, right? Simply speaking about this slide is that when you have multi-nully distribution, when you sum probability of all the class together, you get the value equal 1, just like the rest, right? But there can be multiple outcomes. Then it comes to this Gaussian distribution. Like Gaussian distribution is the distribution over the real number, which can be explained by this. This is the exponential square that create the bell shape, and the sigma square here, because it is in the denominator, it would control the width of the mountain of the shape here, and mu, because it is minus with x here, this will control the location of x, and it will shift the bell shape to the exact location of mu. Right, so these are the parameters of the normal distribution. Normal distribution looks like this. You have the inflection point at mu plus and minus sigma, and you have the maximum here as mu. Okay, this is for one variable. When you have multiple variables, like many times we want to predict not just one values in regression, especially when you use deep learning, want to predict like a set of values. Right, we have this. We can represent it as the multivariate normal distribution. Okay, so just like normal distribution, but this time we have this as a vector x, and the sigma refer to the covariance matrix rather than just variance. But everything else are the same. Okay, this is multivariate normal distribution. Okay, so mathematically, when we perform deep learning and we have multiple linear output, we are essentially creating something like this one out. Sometimes we want to predict data that is not normal. Right? The data may comes from a distribution other than normal. Like if we want to predict the time, or we want to predict the time value, it may have the behavior of the exponential distribution. Exponential distribution would have value lower when the value of p higher. That means this, you can use this to represent something like the survival probability of the patient, the survival probability of the device, and that can be represented as the exponential distribution. Laplace distribution is more of an, I would say, the generalized framework of the normal distribution, because you can see that instead of having square, you have absolute, right? Absolute. So by having absolute, it will create a sharp peak. This is called Laplace distribution. Okay. In the book, sometimes they will use this, but we will not see it again, I think, because I will just disregard this complicated distribution out. There is this distribution that is quite useful. This is called the Dirac distribution, or the delta function. Dirac distribution represents the impulse, right? It usually is drawn as an arrow upward here of delta x, and this is coming from squeezing a square matrix to the infinitesimal width. So once you squeeze it into an infinitesimal width, the height would be 1 over the width, which will be infinity. Right? So this is called Dirac distribution, often used to represent something that occurs just at the moment, an impulse. Okay, right. These distributions can be mixed. You can have a mixture of distribution, and the mixture of distribution can be combined. Like multi-nully, and the other can be combined by having the distribution and the proportion of data. Like the data can come from a mixture of distribution when you combine things together. particularly for the continuous data. You can have part of the data come from normal distribution, another part of the data come from exponential distribution to represent one set of data, right? So the data can be mixed. In neural network, we will not specify this directly. Usually we will create a pathway, or we will create an architecture of the model so that our model would learn from example from pairs of data, and then it would learn this distinction between the patterns, right? So these are about distributions. Now let's look further. When do we use this probability, and how do we use them in the machine learning, right? This is a critical rule. It's called Bayes rule, critical rule in machine learning, right? This rule indicates that when you know nothing, you have certain hypothesis that thing would occur. We call that the prior probability. This prior probability, or PH, once combined with the likelihood that evidence E would occur in the condition of H, when you combine them together and then divided by the prior of the evidence itself, you get this posterior probability, or the probability after considering evidence. So think about detective. Detective might have certain assumptions on who would be the culprit, right, in solving crime, right? Once the detective know more evidence, right, this likelihood, no more evidence, this probability would be updated, right? It would be updated so that the posterior probability would reflect the change of the belief through the evidence that are observed, right? So this is Bayes rule. In machine learning, think about it this way. We have prior probability, or the class you want to predict. We know the data and the class have certain relationship. Combining them, we would have the probability of predict class after knowing data, right? And that allows us to make the postulation, or make the conclusion about the data, or about the class that we want, about the prediction that we want to do based on the data that we observed so far, right? These are the Bayes rules, right? So this is, you can see that this is very important in machine learning. We will see it again for sure. Now it comes to my next is the lovely function that you see often, and later in this class you have a chance to take a derivative of this function, right? Calculate the dip of the function, because it is quite crucial in the classic neural network, right? This is called the logistic function, or the sigmoid function. The logistic function has the form like this. This is 1 over 1 plus exponential of minus x. You can think of this x as two ways. If x decrease to minus infinity, what would happen? X decrease to minus infinity. exp would be large. A large exp here would make the function here equal 0. If x is more than if x approach infinity, exp of the exponential of minus x would be diminished to 0, and the result will be 1 over 1. This is equaling 1, right? So what we see here is that there is a certain transition, a smooth transition from 0 to 1, and this can be used to represent the output of the neural network when we have like binary classification. But this function is slow. Well, you will see later in optimizing parameters of neural network, this function is slow because things occur if the value is here, then there's no gradient at all. We will talk about that later on, right? So there's another useful function called the soft plus function. The soft plus function is just like this is soft plus function. So instead of having the value approach 1, the soft plus has the value, this value, when x is large, then the effect of 1 will be diminished. You have log and exp, which can be thought of as a linear function, right? So soft plus kind of become linear, afterwards. Right? And this has arisen to be a very popular function right now. And there is a function that is simpler than the above. The soft plus is called the ReLU. We will take a look at this function later. Rectify linear unit, ReLU. And this function is a lot simpler than the above, because this is like you have the value between max and x. If the value is more than 0, then you have value of x, otherwise you have value of 0. Right? So the ReLU function looks like this. Okay, just like soft plus function. These functions have certain nice properties. Okay. Some of these properties will be revisited later on. For example, the derivative of the sigmoid equal the sigmoid itself and 1 minus sigmoid. Why is that? We'll take a look at that when we learn about backpropagation, and the reason why we need to take derivative of that later on as well. And 1 minus sigmoid is sigmoid of minus value of that value, and derivative of the soft plus is actually sigmoid. So there are certain relationship between the two, right? So we'll not dig deeper than this. Okay, so just there are certain relationships. The most important one would be this one. This one we'll revisit it again later on. Okay, now it comes to the last section on information theories. Information theories play a major part in a lot of equations in deep learning that you see, and also in machine learning as well. Like when you look at algorithm, a simple algorithm known as decision tree, right? In the decision trees, there is the idea that you can find the variables by partitioning the data based on the base variable. To find the base variable, you need to find something like information gain, how much gain of information that value gives you. And the basic idea is to write for the Shannon information gain, calculate on entropy, and there are those concepts that are important in machine learning, right? How to identify variables that are important and such. Okay, so information theory is the theory underlying the likelihood that event will occur, right? We want to learn the event, how unlikely event would occur. We need to find like the informative attributes that allow us to learn that. Right? So there are certain nature about this unlikely event. The likely event would have low information content, while the less likely event would have higher information content, because you want to kind of narrow down to find those less likely events. And when you have independent event, the information should be additive, right? You can add information from independent event together to get more information, right? With this in mind, let's take a look at a few slides here. This will indicate the rules of in the information theory that are quite useful in deep learning. Right? The first one is self-information. We can define the self-information, right? The information about itself by taking the minus of log. Okay, when we have property of px, we take the minus of log of px. We get the kind of the amount of information of this this event, right? This self-information is quite when we take a look at it alone, it doesn't mean anything, right? But when we extend the theory further and considering self-information, just one single outcome doesn't mean anything. But if you have two outcomes, the self-information becomes the expected value, because you have two outcomes, you have two probability. Then it becomes the expected value of the information x which is the expected value minus expected value of the log of px. This is actually called the Shannon entropy, right? The Shannon entropy can be calculated from the formula I think it's P log P and plus 1 minus P log of 1 minus P for two classes. This is log 2. Right. So here is the expected value of the information, of the cell information. So instead of having just the value alone, we have the value in this form. I think it is correct, but let me check. Let me check it here. Does it have the minus sign? Yeah, it does have the minus sign as well. Yeah, I forgot this minus sign. Minus. Right, minus sign. So you can see that the cell information of the event when you have like two outcomes, it now become the foundation of the Shannon entropy used in the technique like decision tree and random forest and Woods tree order and the tree-based technique. The behavior, it will be like this one. That is, if you consider the case that P is 1. When P is 1, and the log of 1, this would be 0. If P is 1, then 1 minus P would be 0. That make everything become 0. If P is 0, 0 times anything would be 0. And 1 minus P would be 1. And log 1 minus P would be 0. And then it's 0 again. So the value will be maximum at the P equals 0.5, right? It will be maximum here. Right? This is Shannon entropy. Okay, high entropy when you have a mixture of the class, right? So this is the concept that is like the foundation of entropy, and we will see it play roles later on in the mathematical foundation of deep learning. Okay, the last one is the Kaubach-Lieber divergence, the KL divergence. KL divergence indicate the ratio. Actually, it's the ratio between the probability, right, of two. Or actually, you take a look at this one. It will be the information of the ratio, right, between the two. And because of log of the ratio, this become the minus. And again, this is the foundation of the information gain. That is taking the entropy of the parent and then minus the entropy of the children, and then you can estimate the gain of information. We will take a look at KL ratio again later on as well when we considering the mathematical part of deep learning. Right. So, but just so you know that these exist, I would suggest everyone review the content in the book. Although I must admit that the book assumes that you need to have a lot of backgrounds in mathematics to kind of understand these things, right? But anyway, I suggest you read this, and if you don't understand, try to find references and then dig further. All right. So these are everything for today. Today we have reviewed the linear algebra, probability, and information theories. Right? The concepts that would play major roles in the understanding of the deep learning and the underlying technique. When you review the paper, I'm sure that you will encounter this equation again. So don't hesitate to come back to this concepts when you do the term paper review and refer anything that you see similar to this to the original concept here. All right. Next time we will start learning about the basic concept of machine learning, I think. Next time we will take a look at the okay. Let's see. No. The term paper review is not the assignment. The term paper review is the project. Okay, here we have 5 assignments on each of these, right? And you also have this research presentation that you need to pick one paper. It can be a conference paper, it can be a journal paper, and I want you to explain the architecture and the mathematical foundation of those work, right? That would occur at the end of the semester here, the research presentation 1 and 2. Okay. Next time we will start learning about the learning topic. We will start with the gradient-based optimization. Now you have a chance to write a program, right? And then we'll also take a look at the underlying, like how the logistic regression learn, and the loss function of the logistic regression, how does it form, and then we'll come back to these concept again, the concept about this callback leader, and also about this Shannon entropy in the estimation of the loss function in the logistic regression. Okay, so again, for those of you who want this link, actually in the syllabus I also have this Zoom link. You can look at the link here, and there it contains topics and the date. And here, because we will need to skip one lecture, okay, on the 7th of September, it is decided to be the holiday. I will try to combine topics a bit, but let's see, maybe autoencoder. I'll try to combine autoencoder with either of these, or with the embedding, right? So because concepts are quite similar, there, autoencoder and embedding. Yeah, I probably combine the two together here, or maybe shift it down, and then you have to cover the advanced architecture by yourself. Right, let's decide that later. Right. So the next time will be gradient-based optimization, and it will be the start of the your first assignment. Okay, that you have to write the gradient-based optimization in that lecture. Okay. We have another question. The assignments start from next week onward. Right. You have about 2 weeks to do your assignments for each of that. Right. So there will be 5 assignments. Performing gradient-based optimization. This start from this, and then performing the backpropagation feed-forward network, and afterward the convolutional network here, and the recurrent network. And finally, the advanced architecture, that you can choose what architecture you want to implement, and then do it that. Now, it doesn't have to be hard. You can use the same data that we have, but try to do it in differently. Like you can use using attention. You can use the armies. You can use create transformer, doing sequence to sequence on a simple data set. Right, and this should be all for what we will cover here. So that's it. Any more questions? If not, let's say good night to everyone here. All right, so good night. See you again next week. All right, next week we will start learning about optimization, okay, which plays major roles in deep learning. Right, so everyone, see you next week.